stability. And also we have mentioned that the rotor angle stability is of three types: steady state stability, dynamic stability, and transient stability. So here in this course, we shall we shall discuss about rotor angle stability only, not the voltage stability, because voltage stability analysis involves detailed discussions or detailed representation of different components. That's why it will not be discussed here. Rather, we shall know what is the voltage stability problem and how it can be actually overcome. So, basic things we have discussed. Some more details we shall be discussing at the end of this chapter. Okay. So we have mentioned about steady state stability and dynamic stability. Difference between the steady state stability and dynamic stability also was mentioned. Basically, the steady state stability is a theoretical concept, is a theoretical type of stability where if you change the uh, actually load very slowly, such that you can ignore the oscillation of the rotor, then the limit of or the maximum power that can be transferred from the machine to the power system is the limit of the steady state stability. So basically what happens whenever you actually change some load, when you switch on or switch off some load, all obviously there will be some disturbances, there will be some oscillation of the rotor, and therefore this form of stability that we mention in case of steady state stability will actually never occur in power system. But since this indicates the maximum power transfer capacity of the system, maximum power handling capacity of the system, that's why steady state stability has also some importance in respect of the maximum loading capacity of the system. Okay, that has been mentioned. And also we have mentioned what is the dynamic stability. Basically, dynamic stability is the practical form of steady state stability. Because of small change in demand, already there is some oscillation in the system, already there is some disturbance in the system, and to overcome the effect of this load change, the controllers installed in power system, controller installed along with the generators, they will try to overcome the bad effects of the load change. So what are these bad effects? Basically, change in terminal voltage. Okay, change in terminal voltage, change in frequency, all these things. So already we have mentioned about, we have studied about the governor. Governor will always try to adjust the frequency. Then controllers, excitation controllers, they will try to maintain the terminal voltage constant by changing the excitation, by changing the field current. And this field current is basically this excitation controller is the main, you can say, the source of uh, um, dynamic instability in power system, because due to the continuous adjustment of the field current, there will be some disturbances imposed on the system. Okay? And these disturbances will again cause some oscillation in the generator rotor. As a result, power system always will be in quasi steady state. It will never be in a steady state condition. Okay, so there are some oscillations, and because of the impact of the excitation controller, it may so happen that the damping of the power system, damping of generator will become negative. Okay, that means what is the impact of this negative damping? Instead of dying down of the oscillations, it will rather grow up. Oscillation generally, because of the effect of damping, will die down and the steady state will be arrived at. But if the damping is negative, the oscillation will grow continuously. And from a small oscillation, small disturbances, it will create initially very small oscillations. But that oscillation will grow. Gradually, it will increase cycle after cycle, and this may lead to the instability of power system. So this form of instability is the dynamic instability, and this problem is called the dynamic stability problem. Okay, so again, dynamic stability problem, because these involve small oscillation. you can actually linearize the system, and you have to develop linearized model of power system component, including the generator, including the excitation system, governor, field circuit, and also different controllers. So analysis will be much involved, and therefore we shall also not discuss dynamic stability. We shall also not discuss the analysis of dynamic stability in details here. Rather, we shall be discussing the transient stability problem. What is the transient stability problem? This is the stability problem because of the effect of large disturbances. Okay, when there are large disturbances in the form of fault, because large disturbances cannot be from load changes. Load changes will be small with respect to the capacity of the system. Magnitude of system loads are very very small, so small loads will be switched on, they will be switched off. So because of that, only a very small change in active power will be there, and as a result there will be very small oscillations introduced into the power system. These are responsible for the dynamic stability problem. But when fault occurs in power system, what will happen because of a fault? So the power generated by the generator will not be able to actually flow through the transmission lines. As a result, there will be large difference between the input power to the generator and output power to the generator, because output cannot flow through the transmission line. So where it will go? It will go to increase the speed of the generator. It will go to increase the stored kinetic energy of the generator. As a result, there will be another type of problem that is called the transient stability problem, and the system may lose its stability. Okay, system may lose its synchronism. So we shall discuss this problem in details here. So, if we want to define it, so it is the capability of synchronous machine of a power system to remain in synchronism when subject to a severe transient disturbance. Transient disturbance means sudden disturbance, okay, such as short circuit fault followed by its removal. Short circuit fault. When short circuit fault occurs, why the disturbance come? Because say at the terminal of the generator, a fault has been created. So generator, obviously from the terminal, there are transmission lines. So power delivered by the generator was flowing through the transmission lines. Now, if fault occurs at the terminal, that means at the bus bar or at one of the line end uh, of that connected to the generator bus, one of the lines that are connected to the generator bus. So if the fault occurs there, so what will happen? Voltage at the fault location, if it is three-phase fault, for simplicity say, if it is three-phase fault, so voltage at the fault location will become zero, and since the terminal voltage of the generator is zero, obviously power cannot flow through the transmission line. Okay, so this creates a major difference, major disturbance between the input and output of the generator, because previously the power was flowing out of the generators, but now the power cannot flow. But obviously, as the fault occurs, there is no corresponding change in the input to the generator. So input remains same, but the output uh, cannot flow. The power cannot flow out of the generator. So this creates a major difference. Now, sometimes what will happen if the short circuit occurs? So there are circuit breakers connected and relays, obviously, to identify the fault. There are circuit breakers and relays means protective systems installed in the power system. This protective system will identify that there was abnormal current flowing, because if short circuit occurs, current will rise abruptly. Why it will rise abruptly? Because voltage was the normal voltage, it is becoming zero means obviously this voltage is dropping somewhere, so it is dropping in the fault impedance. So a large current is flowing. So the relay or the protective system connected with the power system, they will identify that there is a large increase in the current flowing out of the generator, large increase in the current flowing through the transmission line. So this is not an abnormal operating condition, this is an abnormal operating condition. They will identify it and they will send signal to the circuit breakers. The circuit breakers are basically switches. mechanical switches. The circuit breakers, after getting signal from the relays, they will open their contacts. So faulty line will be isolated, will be disconnected from the system. So when the faulty line is disconnected, now say fault has been removed, but power will now flow through other lines. As the power is trying to flow through other lines, then those lines may become overloaded. Those lines may again be isolated by the circuit breaker because the corresponding relay they may identify this situation as an overloading condition or as a fault even. Okay, so other lines also will be overloaded, disconnected. So as a result, in this way, it may show up in that the power input to the generator and power output from the generator, there was a major difference between these two, and because of this difference and the consequences generated from this may result in a situation where the system may lose synchronism. Okay, that means the cause of this loss of synchronism is the large disturbance, large change in the output power from the generator. So when large disturbance takes place, large disturbance of power takes place, active power takes place, then the problem that is generated is called the problem of transient stability. Okay, so, how to analyze this type of stability? Analysis involves the solution of nonlinear differential and algebraic equation. Why nonlinear differential equation? Because differential equations, we shall see later on that, we shall have to represent the generator, basically the rotor of the generator. Because if the disturbance occurs, then obviously there will be a change in the generator. So, rotor dynamics has to be represented. Rotor dynamics has to be modeled. That rotor dynamics will be modeled, or rotor dynamics will be possible to be modeled with the help of differential equation. And differential equations are obviously nonlinear differential equations, and along with some algebraic equation. Why algebraic equation? Because you will be actually calculating the power flow through the transmission line, power flow through the system. So, along with that differential equations, which will be representing the generators in power system, and not there is not a single generator connected to a power system. There are large number of generators connected to the power system, and when a fault occurs, obviously there will be the change in speed in all the generators. So all the generators of the power system are to be represented. So a large number of differential equations are to be solved. Not only this, you have to solve the power flow problem, how actually power is flowing through the transmission lines, and these lines are basically the algebra represented by algebraic equation. That's why differential as well as algebraic equations are to be solved. Okay, so the problem is a major problem. The analysis also is quite difficult analysis, because a good number of algebraic equations, a good number of nonlinear differential equations are to be solved to solve the transient stability problem. Okay. So if the system becomes stable, then how we shall be identifying that? How should we be understanding that system will be becoming stable? Or if it is unstable, what will be the indication that system is becoming unstable? So to know that, you see that in stable case, what will happen? The rotor angle increases to a maximum. Generally, you have to solve this differential equation. Solving this differential equation, and along with that the algebraic equation, you will be actually obtaining the variation of rotor angle with time. Okay, so if you solve those equations, you'll see that rotor angle will actually increase to a maximum and then decrease and oscillates with decreasing amplitude until it reaches a steady state like this. Rotor angle will increase and then it will decrease, and gradually it will oscillate with lower and lower peak. The initial peak is highest. Then there are smaller peaks. Gradually, smaller and smaller peak will be obtained. That means oscillations is dying down. Okay, so this will indicate that the system is becoming stable. That means you have to solve for this differential equation to obtain the value of the rotor angle as time passes. So instead of the solution of the rotor angle will start when the disturbance has been initiated. After that, we will be solving delta with respect to t. Delta is the rotor angle, t is the time. So, and we'll be plotting the or we'll be obtaining the variation of rotor angle. So, delta will become maximum and then decrease, then smaller oscillations will be there, and finally a new steady state will be arrived. Okay. So, in stable case, the rotor angle increases to a maximum, then decreases and oscillates with decreasing amplitude until it reaches a steady state. Okay, this is one form of indication when the system will become stable. The post-disturbance steady state may differ from that at the pre-disturbance condition. What is the meaning? Post-disturbance steady state means a fault has occurred. Then, because of the fault, say the system became stable, a disturbance was there was change in the rotor speed, but finally say rotor speed has achieved synchronous speed again. Okay, there are some oscillations and a new steady state is arrived at. There is no guarantee that the new steady state and the steady state before the disturbance they will be same. That means what we want to say here is that the delta of the machine, delta of the rotor before the disturbance and delta after the disturbance at the new steady state, they may be different. Okay, it will depend upon the system condition, it will depend upon the type of disturbance, it will depend on the situation, what are the control applied and what are the changes in the system took place. So these will decide whether the new steady state and old steady state will be different or not. Okay, so they may become different. In one type of unstable case, the rotor angle continues to increase steadily until synchronism is lost. You see this one. Rotor time continues to increase until the stability. This obviously is an indication that the angle is growing on continuously. When the angle may grow on continuously, delta is increasing. Obviously, rotor angle will increase. How we measure the rotor angle? It is the angle between the terminal voltage and the induced EMF. Obviously, we have seen that when we have seen the phasor diagram of the synchronous generator, cylindrical rotor synchronous generator, we have seen that the position of the induced EMF is along the quadrature axis of the rotor. So we can say that if the rotor position changes, then only delta will be changing. Okay, and when the rotor position can change, obviously when there is a change in the speed of the generator. So after the disturbance, if the speed of the generator increases, then what will happen? Then the you see that terminal voltage it is connected to the power system in infinite bus. Infinite bus means it is always its frequency is constant. So angular velocity of the power system voltage that is synchronous, but the rotor speed that is synchronous when the system is in stable condition. When there is disturbance, the rotor speed may increase, rotor speed may decrease. So if the rotor speed increases, what will happen? There will be increase in the value of delta. Okay, so when the rotor is moving at a faster speed, obviously then delta will be increasing. So when delta increases continuously, it indicates that speed is increasing continuously. It is above synchronous and it is not becoming synchronous again. It is not becoming below synchronous again. Okay, so if the rotor speed increases continuously, it is indicated by the value of delta. Delta also will go on increasing, and this indicates that system is losing stability. It will not be possible to restore it. It will not be able to restore the synchronism of the system. Okay, so this is indicated the instability, indicating the instability of the power system. So in one type of unstable case, the rotor angle continues to increase steadily until synchronism is lost. So as I have mentioned about that figure. Okay. This form of stability or instability is referred to as fast swing stability or instability. Okay. So this is one case, stable unstable condition. This is one case, stable condition. What happens here? Here, rotor angle increases and then decreases. Decreases with lower amplitude again increases with lower, still lower amplitude, and again decreases still lower amplitude. In this way, gradually synchronism is achieved. Here, rotor angle is increasing continuously. So here you see that in this case, if you see the first swing, what is the meaning of first swing? Rotor angle is increasing and then decreasing and then increasing again. So, one swing is completed. It then again increases and decreases. But here the indication is such that continuously you see that gradually the peaks are becoming lower. That means it will become synchronous again. The steady state will be obtained again. So this, for this form of stability, for this form of disturbance, you can say that you can assess the stability of the power system if you look at the first swing. How? If you see that rotor angle is increasing and then decreasing, okay, then it is an indication that the system will become stable because it is increasing and then decreasing. Increasing means speed is becoming above synchronous, decreasing means speed is moving towards synchronous and becoming below synchronous. Okay, again increasing means again the speed is becoming above synchronous. So if the system oscillation is such that consecutive swings will be of lower and lower amplitude, then you can see that stability can be assessed from the first swing. Similarly, in this case also, rotor angle is growing, it is not decreasing. So here also, by seeing the initial swing or by observing the first swing, here the first swing is not completed because rotor angle is increasing continuously. So in this case and this case, that means here in case 1 and in case 2, you can say that by observing the first swing or observing the initial period of the variation of delta, you can say whether the system will be able to restore synchronous speed or not. Okay, is it clear? That means that whether the system will be able to restore synchronism, whether the system will be able to maintain synchronism, okay, it will be obvious from the observation of the first swing, here in this case when the system is stable, and also here in this case when the system is unstable. Okay, so in this case, this form of stability or instability, we have mentioned both, is referred to as fast swing stability or instability. That means here, by observing the first swing, you can say that system will become stable, or by observing the first swing, you can say that the system will become unstable. Okay, but there are other forms of instability or stability also may be possible. What are these instability? In the other type of unstable cases, the system is stable in the first swing. Okay, that means first swing delta is increasing, reaching maximum and then decreasing again. Speed is increasing, become above synchronous and then decreasing, becoming synchronous again and then becoming less than synchronous again. But in the subsequent swing, the amplitude may increase. It may exceed the first swing case. Okay, is stable in the first swing, but becomes unstable as a result of growing oscillation in the subsequent stages. That means in the subsequent swings, the oscillation may grow. Okay, acceleration may go because of many reasons. This generally occurs when the post-disturbance steady state itself is small signal unstable. That means in the post-disturbance steady state means, that means system would have reached in a situation in a steady state where a small change in demand would have caused the system to become unstable in the sense of dynamic stability. Okay, that means when the system becomes uh, unstable, it becomes because of small disturbances. We call that this is the dynamic stability problem. And if the system becomes unstable due to the small disturbances, so we can say that system is dynamically unstable. Okay, so after the first swing, system could have reached to a steady state situation when the next steady state is actually dynamically unstable. This is the indication of this type of swing. Okay, so in large power system, transient instability may not always occur at first swing. Now, nowadays power systems are actually vast. Okay, that were many power stations. Okay, many power stations, and if the fault occurs, then actually impact of the fault on the generators will depend upon the location of the fault. Obviously, the maximum impact will occur on the generator which is closest to the fault. Okay, but to the generators which are far away, the impact will be somewhat different. It will not be similar impact always. Okay, so in power system, large power systems, transient instability may not always occur at the first swing. It could be the result of superposition of several modes of oscillations causing large excursion of rotor angle beyond the first swing. So these things are somewhat, I should say that somewhat complicated terms we are saying, complicated words we are saying now to you, because actually in power system what will occur? What will happen? There are so many machines, so many generators connected, and some of the generators may be such that they will be swinging together. Okay, that means they will be oscillating together because of their location, proximity of their location. Okay, they will be swinging together, but some generators may swing with respect to other generators as well. So in this way there will be different mode of oscillation. That means there will be oscillation between group of generators. Okay, there may be oscillations between two generators or between two groups of generators. Okay, so these are the therefore so many modes, so many types, so many types of oscillations may actually occur in power system because there are so many dynamic devices, so many generators connected in power system because of the impact of rotor, impact of the exciter, because of the impact of the governor, because of the inertia of the generator, because of the location of the generator. There may be different types of swing. Okay, there are large transmission lines through which large power is flowing, but it is an interconnected power system. It may so happen that at the one end of the generators they are swinging with respect to the generator connected at the other end of the transmission line. Okay, so there are so-called inter-area oscillations. There are so-called swing between the groups of generators. Okay, between the coherent group of generators. So these things are always there because power system is very large. There are so many generators, there are many types of oscillations are there. So when the fault occurs, when the disturbance occurs to a generator, maybe in the first swing generator could manage to show the symptom of maintaining synchronism. It could maintain synchronism that in the first swing the delta increased and then it was decreasing. Okay, but subsequently because of the impact of other swings, it may so happen that finally the generator may not be able to maintain synchronism. So instability may occur in that way also. Okay, this is what is being stated in these sentences. In large power system, transient instability may not always occur at first swing. It could be a result of superposition of several modes of oscillation, causing large excursion of rotor angle beyond the first swing. That means it is not always true that the first swing will indicate that the system will become stable. In simple cases, this will be the indicator. First swing will show that the system is stable, then it means it will be stable. But in large power system means they are more complicated. There, it may show up that the system is stable in the first swing, but subsequently, because of the impact of other generators, because of the impact of other oscillations, other swings, prevailing in the power system, the stability of the system and the stability of the generator may be lost. Okay. So in transient stability studies, the study period is of interest is usually limited to 3 to 5 seconds. It is a standard. Generally, you have to solve the differential equation to solve the stability problem, whether the system will be stable or not. To analyze this, to see this, you have to actually solve the differential equation. How long will you be solving? For what time? Obviously, you will be solving using some numerical techniques, and delta will be you will observe the variation of delta as time passes. How long will be solving the differential equation for what? How much of time? It will be from 3 to 5 seconds, because if the system is stable, generally it will be indicated in this time. 3 to 5 seconds will be sufficient to say whether the system will be stable or not. Why 3 to 5 seconds? Because you see that 3 to 5 seconds, obviously it will not be a case of first swing, subsequent swings also will be appearing here. Following the disturbance, okay, 3 to 5 seconds following the disturbance, although it may extend to about 10 seconds, because then, because of large disturbances, because of the impact of other swings, other swing modes, so those, whether those swings are actually impacting the stability of the generator or not, to know this, sometimes it may have to be carried up to 10 seconds as well. For very large system with dominant inter-area mode. Inter-area mean, because basically inter-area mean basically a section of power system is called an area. Okay, in case of basically what the frequency control analysis, actually you should have mentioned about the area. That means the generators under one control, under the control of an administration, you can say that technical administration, that is called a single area. So between the generators of different areas, there may again be swing, because the frequency is being controlled by one authority here, frequency is being controlled by another authority here. Say across a transmission line, across a tie line, these lines are called. Obviously, there may be swing, there may be oscillations. Okay, to include the, to actually take into effect of these oscillations prevailing in power system for particularly complicated large power system, the stability analysis may have to be carried up to 10 seconds for those large power system. Okay, for very large system with dominant inter-area mode. That means where the inter-area mode, dominant inter-area mode means where the inter-area between this area and that area, this oscillation is rather strong, because these oscillations may cause impact on the stability of another generator that is again under swing because of some other disturbances. Okay, so these actually, for analyzing the impact of large disturbances, for analyzing the stability problem of power system, you have to solve the differential equation and algebraic equation, and quite for some time it has to be solved. But here, what we are mentioning all these things, because we shall be actually employing a very simple method here for stability analysis, and we shall be observing only the first swing stability, not the subsequent swing, because we shall not be going into the solution of differential and algebraic equation here in this course. Maybe later on in some other course we may be observing those things, but here we shall be utilizing some simple method for analyzing the stability problem, for understanding the stability problem. There we shall be observing only the, or it shall be analyzing only the first swing and deciding whether the system is stable or not. But when the first swing you can use to decide whether stability will be obtained or not, only on those simple cases where inter-area oscillations or oscillations between group of generators is not there. So we shall be assuming that in our generator, in our case, we are ignoring the inter-area oscillations and other oscillations we are not considering. We are only considering the impact of the disturbance on the generator that we are considering, and the remaining power system, that means we are considering them that to be an infinite bus. That means we shall be considering a power system where a generator is connected to infinite bus. Why we have mentioned all these cases? Because actually an infinite bus intrusions does not occur, does not exist. Okay, if you consider the actual power system, then you have to consider all these complications. So in real stability analysis, you have to include all these things. But to start with, we shall be assuming that our power system is simple. It may be represented by a single generator connected to infinite bus, and there we may consider that the system outside the generator we are considering can be represented by a single bus, which is the infinite bus. Means it is moving at, it is maintaining its synchronous speed, it is maintaining synchronous frequency. Okay, So this is why we have mentioned all these things to actually differentiate between the uh, infinite bus concept and the actual situation where the generator should be connected. Okay. Now, all right, could you understand all these things? Could you follow whatever I actually mentioned here, or any question you want to make here?
No, sir, understood.
I could not hear. Please loudly.
No, sir, no doubts.
Okay. Okay. Then now let us talk about the stability limit. We shall be gradually moving towards the representation of generator for stability analysis. But before that, uh, let us talk about stability limit first. Okay. The power that the system can deliver, that we have already mentioned, that the power that the system can deliver without the loss of stability is called the stability limit. Obviously, how much power the system can deliver without loss of synchronism, it is the stability limit. In case of very small disturbances, or in case of steady state stability that we have mentioned previously, it is the peak of the power angle curve. Because we are ignoring all oscillations, so limit of power transfer is the angle delta equal to 90 degree, and at delta equal to 90 degree, the mm, obviously the peak of the power angle curve is reached. So here the stability limit is the power corresponding to the peak of the power angle curve. Okay, since the steady state stability neglects oscillation, its limit is the maximum power transfer capacity of the system that I have mentioned. Okay. Steady state stability does not depend upon the existing operating state of the power system. So it is very important, this statement. What we are saying here, the you see that steady state stability limit, it is fixed. How much it is? It is corresponding to the peak of the power angle curve. What is the value of the peak of the power angle curve? That gives you the steady state stability limit. You need not bother about the present operating condition, how much power the generator is delivering now. Okay, that is not at all important. What is the delta value? That is now. That is not also important. What is important? What is the what is the value of the power at delta equal to 90 degree? If it is a cylindrical rotor machine, then the peak of the power angle curve will represent the stability limit, and therefore this limit does not depends upon the present operating condition. Okay, that's why steady state stability limit does not depend upon the operating condition of the system. It is irrespective of the operating condition, the limit is fixed. But what happens to the transient stability limit? Transient stability limit depends upon the present operating condition, amount of disturbance, and also the controls applied for maintaining the stability. We shall be explaining all these things, but simply before we reach enter into the problem, let us just mention what are the actually how what is the difference between the steady state stability and the transient stability. So transient stability, we shall see that it depends upon the present operating condition. It depends upon the magnitude of disturbance. How much is the magnitude? How much is the power involved in the disturbance? And also, it will depend upon the control you are applying for bringing the synchronous speed back in the system. Okay. So, what is the control applied? How much is the disturbance? What is the present operating condition? All these three are important in respect of transient stability, but nothing is important. None of these are important actually in this case of steady state stability limit. It is fixed. So you can say that obviously transient stability limit cannot have a fixed value because it depends upon the present operating condition, because it depends upon the magnitude of disturbance, and also because it depends upon the control you are applying. So since these things actually there may be many types of many present operating condition may change depending upon the present loading condition. Amount of disturbance, it will depend upon the type of fault occurring in the power system. And what is the control? That obviously will depend upon the actual operating condition. Depending upon the operating condition, you will be applying control. Then you will be knowing whether the system will be stable or not. So you see that transient stability limit cannot actually be a fixed limit. It is varied limit, And what is the limit? It depends upon all these three factors. The limit of transient stability depends upon the speed of the circuit breakers and relays. Okay, I have mentioned that there are protective devices. What are the function of protective devices? These protective devices basically identify the faults and isolate the faulty equipment from the system. Disconnect the faulty equipment from the system. So if the faulty equipment is disconnected, that means you can say the source of problem is disconnected. Okay, so it is important how fast you are identifying the fault and how fast you are disconnecting the faulty equipment from the system. That also will actually have some influence on the stability of the power system. So, limit of transient stability depends upon the speed of circuit breakers and relays. We shall see how it is depending upon all these things. We shall see by using some criteria later on. We shall see this. First, clearance of fault and excitation control through automatic voltage regulator. There are excitation controllers connected with the generator. Again, these excitation controller will be employed in case of disturbances to change the field current, okay, to regulate the terminal voltage. And this change in the field current, that means controlling of field current, also has some impact on the ability of the generator to restore synchronism. Okay, so it will depend upon this also. Use of braking resistors. These are some methods for improving the stability. Braking resistor, fast valving, and use of HBD sealing. So we shall not later further skip these things, this discussion now, and we shall be discussing later on when we actually are in a position to analyze the stability. Therefore, then only I shall be discussing these things. Okay, and dynamic stability, how it can be improved. Then also later on we shall be discussing all these things. So there are different methods for improving the dynamic stability and transient stability. So you see that only the steady state stability limit is fixed. Neither the dynamic stability limit nor the transient stability limit are having a fixed value, because all these things are depending upon the operating condition, current operating condition, magnitude of disturbance, and the type of controls you will be applying to restore the synchronism, restore the synchronous speed to the power system. Okay, so only the steady state stability limit has a fixed value, and it is corresponding to the peak of the power angle curve only. Okay, now let us now, okay, so all these discussions we have made only to give you some idea regarding the problem, regarding the difference between the steady state, dynamic, and transient stability problem. And now let us enter into the analysis of the stability problem. Okay, so we shall be now developing a model to represent the generator, to represent the rather dynamics of the generator rotor. Okay, basically we shall be representing the dynamics of the rotor of the synchronous machine, and the equation that are all the model that we will be developing, that we shall be developing, will be called the swing equation, because this equation represents the swing, or this represent equation represent the oscillation of the generator. This will be utilized, or this will be able, this equation will be able to represent the oscillation of the generator rotor. That's why it is called the swing equation of synchronous generator. Let us assume that Ti, this is the mechanical torque input via shaft from the prime mover. What is the prime mover? Prime mover is the turbine. In case of cylindrical rotor machine, it is the steam turbine. Say you are actually the input torque to the generator rotor, and it is through shaft, through turbine shaft coupled with the generator rotor. Okay, this Ti is being applied. Okay, it is a mechanical torque input, and the torque output is say Te, developed electromagnetic torque is output. What is the, how much power is being delivered at what speed, that will decide how much is the torque delivered, how much the electromagnetic torque. In steady state, what will happen? This mechanical torque input and electrical torque output, these two are same. So in steady state, Ti is equal to Te, because there is generator is rotating in stable condition, speed is synchronous, obviously there is neither acceleration nor deceleration, and the speed of the generator is synchronous. So Ti equal to Te. Torque input, okay, mechanical torque input is equal to electromagnetic torque output. Now, when disturbance takes place, when unbalance takes place between the input and the output, then what happens? Then there is a difference between Ti and Te, and that this difference, say Ti minus Te, input minus output, say this difference is Ta, accelerating torque. So, if it is positive, the generator will accelerate. If it is negative, generator will decelerate. So either there will be acceleration or there will be retardation depending upon whatever the Ti is greater than Te, input is greater than output, or input is less than output. Okay. So this is the condition, and for stable operation and during disturbances, when there will be unbalance between the input and output, say Ti is the accelerating torque and Ti minus Te. Ti may be positive, Ti may be negative. Positive means there will be acceleration, speed will become above synchronous. Negative means there will be deceleration, speed will become below synchronous. Okay, but we know that from the law of mechanics, why to know I alpha equal to Ta. Okay, torque is I into I is moment of inertia, and alpha is a angular acceleration. Angular acceleration. So we can write that moment of inertia into angular acceleration is Ta. All right. This we can write from mechanics. You know that. So actually, this should come here. Huh. So acceleration, angular acceleration. Okay. So angular position is theta. Then alpha, therefore angular acceleration is d2 theta dt2. That means d theta dt. How much is it? Is the speed. Okay. Theta is the rotor position. So what is d theta dt? It is the rotor speed, and d2 theta dt2. Obviously, this is the rotor acceleration. So alpha is d2 theta dt2. So theta is measured with respect to a stationary axis. Say we are measuring theta with respect to a stationary axis. So d theta dt at when the speed is synchronous, you can say that obviously. And then obviously d theta dt with respect to a stationary axis, you can say that ultimately alpha will be equal to 0 when the speed is synchronous. So when, because input and output, the input and output they are same, so with respect to the measuring axis, okay, reference axis, the rotor is at the fixed position. Okay, but when the speed increases, when the speed become above synchronous, when the input and output becomes different, then obviously d theta dt will be non-zero, d2 theta dt2 also will be non-zero. So we shall be analyzing the generator during that condition. So if the rotor position is measured with respect to a rotating axis, say, then theta is omega. This is the situation. Say it is a terminal voltage, it is a induced EMF. Okay, so we can measure the rotor position as theta is measured with respect to stationary axis. So how we can write it? It is omega st plus delta with respect to stationary axis. Obviously, theta is changing, but again, if we measure theta with respect to this moving axis, what is the moving axis? Say it is the terminal voltage. Terminal voltage is the infinite bus voltage. Infinite bus voltage has an angular speed of omega s. Okay, so this also with respect to stationary axis, okay, it is also changing. So what is its position with respect to stationary axis? It is omega st. So what is the position of rotor and rotor with respect to that reference axis? It is omega st plus delta, because this is a moving axis. This is also rotor moving at synchronous speed at steady state. So delta is fixed. Now this is always moving at synchronous speed. Now if it moves at any speed which is either above synchronous or below synchronous, then we can say that theta we can write at omega st plus delta. Delta is the value of, or delta is the angular difference between this E and B. Okay. Now what is d theta dt? It is omega s plus d delta dt. Obviously d theta dt is, so it is a rotor speed omega s plus d theta d delta dt. Okay, delta is the rotor angle with respect to the rotating axis, then it is the rotor position, d theta dt is rotor position, sorry, rotor speed, it is omega s synchronous speed plus the deviation of rotor speed with respect to the rotating axis. Okay, and if you take the double derivative d2 theta dt2, then obviously this is d2 delta dt2. So this being constant becomes the derivative of this becomes zero. So d2 theta dt2 is becoming equal to d2 delta dt2. Okay, and this is the acceleration of the rotor. Okay, so we can write I alpha equal to ta. So we can write I d2 delta dt2 equal to ta, means input torque minus output torque, means what is input torque? Input power is say pi. So input power by omega is ti. T is the electromagnetic torque output. So electrical power output by omega. Again, this is Te. So you can write that Ta equal to Pi by omega minus Pe by omega. Or we can write that like right I omega. Let us bring omega here. I omega d2 delta dt2 equal to Pi minus Pe. Okay. I omega, it is I omega here multiplied this d2 delta dt2 equal to pi minus pe, and I omega is let us write I omega equal to m is the angular momentum, it is the moment of inertia, it is the angular speed, then product of this is called angular momentum. So m d2 delta dt2 equal to pi minus pe, m is the angular momentum, and pi minus p, let us write this as pa, this is difference between input power and output power. So obviously it is responsible acceleration of the rotor, so it is the accelerating power. Okay, the accelerating power rather. Okay, and what is the kinetic energy stored in the generator rotor? You see that K is half I omega square. Okay, or half I omega is m angular momentum, and then again another omega. Okay, so K is half I omega square or equal to half m omega. Okay, so this is nothing but the kinetic energy. It is joule second, and m of unit of m is joule second per radian. Okay, and generally we are representing here it by m, but generally it is more popularly in case of frequency control we have represented generator inertia in terms of h, inertia constant, not in terms of angular momentum, because even for machines of similar design, moment of inertia and momentum, that means I and omega, vary over a wide range with variation in rating. So if the rating of the machine changes, then value of I and value of m, they also change. Therefore, momentum is more conveniently expressed in terms of an inertia constant h. So popularly, instead of mentioning I or M to represent the inertia of the generator, manufacturer generally represent the inertia in terms of H constant, which is defined as, already we know this, stored energy by rating of the machine. So stored energy in megajoule by machine rating in MVA. So this is how H is defined, and generally inertia is represented in this way. So we can actually, so this is how the edge generator inertia is represented. Okay, so we shall be going here later on. Just 1 minute. Okay, so we shall be while actually discussing the solution of the this rotor angles, swing of the generator, basically represented by this equation m d2 delta dt2 equal to pa. So m d2 delta dt2 is pa. It is called the swing equation of the generator rotor. This is a differential equation, second order differential equation. So this is the swing equation, popularly known as. That means the dynamics of the generator rotor is represented by this expression. This is the swing equation, and in order to investigate or in order to analyze the stability of the generator, that means the ability of the generator to see whether it will be able to maintain synchronism or not after a disturbance, what you have to do? You have to solve this equation. M d2 delta dt2 equal to Pa. Generally, value of M is not available, but since this is, we can represent in this way. Okay, but generally, instead of M, people actually use H. Okay, so how H may be represented? So H is actually stored energy in megajoule. That means it is half m omega. Okay, and machine rating is say capacity of the machine. So we have a relation between the H and M. So M will be replaced by H. Okay, so M will be replaced by H from this expression. We shall see this later on. Okay, so while solving, actually when you will be solving, you will be rather writing M in terms of H from this expression, of from this definition of H, where H is stored kinetic energy in megajoule, that means half m omega. Okay, by machine rating. Say machine, the machine rating is G, so half m omega. So m is actually 2gh by omega. 2gh by omega, if you obtain the value of m from this definition of h. So 2gh, the g is the machine rating, so it is half m omega. So 2gh by omega. Omega means the speed of the angular speed of the generator. Okay, that will give you the value of m. So generally, m will be replaced by means of h. But in further discussion, when we shall be solving the or representing talking about the swing equation, we shall be talking in terms of m, because it is popularly this is the form of equation, uh, form that we actually use for representing the swing equation, m dt delta dt2 equal to pa. Now the question is how to solve it. Obviously, we have to solve the differential equation. How to solve this differential equation? Obviously, you will be applying numerical techniques. Okay, because this is a simple method for solving differential equation. So solving differential equation obviously will be rather a difficult job. Why rather a difficult job? Because even if you apply some numerical techniques, then you have to calculate the value of PA. Okay, you have to solve for delta for using different time steps, and many time steps will be required to find out the solution of the swing equation. But that is required for actual analysis of the stability problem. And when you will be analyzing the stability problem for a large power system, when you have a number of generators connected there, then you have to solve for the swing equation for each and every machine. So you see that solution of differential equation, solution of the stability transient stability problem is rather a difficult job. It rather a involved process. Okay, because so many differential equations are to be solved. But here, because now we want to rather, instead of solving this, we want to rather understand the problem of stability. What are the problems involved? How the stability may be improved? What are the factors that actually are having impact on the stability of power system? We are interested to know all this first, and then we shall go for analysis. That's why we shall be rather utilizing some other simple technique to analyze the stability. That technique actually will not be applied for analyzing the stability when we shall be solving the large power system, but for understanding the problem of stability, it is the best approach, you can say. So therefore, we shall be using that approach, and that approach is called the equal area criterion for stability, for transient stability. So we shall be therefore now moving to apply equal area criterion, or to rather derive the equal area criterion for stability analysis, and then we shall be investigating the stability problem with the help of equal area criterion. Okay, so here these expression, these derivations here, we are discussing only to represent the generator rotor, hmm, which is subjected to some disturbances. Where from these disturbances are coming? These disturbances are coming in case of faults in power system, because in case of faults in power system, if the generator was delivering some power, say, and if fault occurs at the terminal of the generator, then that power cannot flow from the generator. So a difference now appears between the input power to the generator and output power from the generator. Now we shall have to see how this difference in power between the input and output of the generator is changing its speed. Okay, and whether this change in power will be sufficient to cause the generator to become unstable. Okay, so this is our focus now. Whether the disturbance that has created a difference between the input to the generator and output power from the generator, whether that disturbance is sufficient to cause the sufficient to make the generator unstable, whether the generator will be able to retain synchronism, whether generator will be able to restore synchronous speed again in the system. Okay, and here our approach will be a simplistic one, because we shall be assuming that the generator is connected to an infinite bus, and the system will become stable if the system is appearing to be stable in the first swing of the rotor. Okay, this will be our approach. But actually, we have seen that we have discussed this thing that the even though the generator is appearing to be stable in the first swing, in the subsequent swing, it may lose synchronism. But that complicacy we shall not be handling for the time being. We shall be assuming that if the generator can maintain synchronism in the first swing, that means if the delta increases first and then decreases, it indicates that in the first swing the generator will be stable. So it will be stable in the subsequent swing as well. So this will be our assumption, and under this assumption, we shall be proceeding to develop the equilibrium criterion. Okay. So for that, now consider a simple system. We shall be developing equilibrium criterion. So now let me know whether you could understand whatever I have discussed so far. More, is there any question you are having now?
Sir, theta equal to omega st plus alpha होता है सर एक बार explain करूँ?
Hello, please actually, so 1 minute. I cannot hear you.
Sir, theta equal to omega st plus
One
alpha.
minute. I shall have to
Okay sir. Okay.
increase the sound here because I could not hear. Okay, please repeat.
Sir, theta equal to omega st plus alpha हो जाएगा ताकि explain करूँ sir.
Acha, omega theta equal to acha. Okay. Basically, what we assume that actually, say theta indicates the rotor position. Why we are bothering about the position of the rotor? Because whenever we have developed the phasor diagram of the generator, this is the part of phasor diagram showing the terminal voltage and the induced EMF. Okay, we have
Okay.
seen that E is along this induced voltage is along the quadrature axis of the generator. Okay, it is
Yes.
along the quadrature axis of the generator rotor. So rotor is rotating, okay, at synchronous speed at steady state. So
Yes sir.
E is along the quadrature axis. Now let us assume that we are measuring theta with respect to some stationary axis. Where is this stationary axis? Say this stationary axis is, say, somewhere in the at the stator of the generator. For say we have put a mark on the stator of the generator, which is the fixed body. Okay, there we have put a mark, and with respect to that mark, we are actually measuring the value of theta. That means measuring the position of the rotor. All right.
Yes.
So theta will be changing with time because generator is rotating at synchronous speed. So even the generator is at steady state, then also theta will be changing with time. And how it will be changing? It will become omega s into t. Okay, omega s into t. Now let us assume that uh, Omega s is the synchronous speed. So at steady state, theta will be equal to omega s into t. Now let us express theta with respect to some stationary axis. What is the stationary axis? This is say the terminal voltage of the generator. And term generator is connected to infinite bus.
Yes.
Infinite bus is a bus where the speed is synchronous, where the frequency is synchronous frequency. So obviously, infinite bus, that voltage will maintain a synchronous frequency, means the angular velocity of that phasor v is a phasor, the angular speed of this phasor is that omega s. Okay,
Yes.
so what is the position of v with respect to that stationary axis which is located at the stator of the generator, that is omega s into t. Okay,
Yes.
so this also is the position of, if we, if the generator is rotor is rotating at synchronous speed, so we can say then if E and V, they are making a constant angle delta, so we can say that at steady state E also you will be making an angle delta with respect to V. So if V is making a position of V is given as omega st with respect to that stationary axis, position of E will be omega st plus delta, because position of E is at an angle delta with respect to B. B position of B is omega st with respect to that stationary axis. Am I clear?
Yes, sir.
Now,
Yes.
now this is the position of the rotor. Okay, or you can say this is the position of the that the rotor means position of the that the quadrature axis of the rotor, say, along which the is lying, along which is lying. Now, what is d theta dt? Derivative of theta with respect to time. Obviously, derivative of theta will be giving us the speed. It was the position, now the speed. So obviously, it will be equal to omega s plus d delta dt. So at steady state means when the rotor rotates at synchronous speed, obviously there will be no variation of delta. So d delta dt will be equal to zero. Means
Yes.
d delta dt equal to zero means the generator rotor is not making any speed with respect to with respect to the infinite bus voltage. Both are at steady state. There is no change in the speed. There is no difference in speed. But at any other speed, obviously d delta dt will have a value. If
Yes.
the generator is rotating at a speed which is above synchronous or which is below synchronous, there will be a non-zero value of d delta dt. Okay, that means d delta dt is the difference in speed between the rotor and the infinite bus voltage. Am I clear?
Yes, sir.
Okay.
Clear.
Now, so it is the synchronous speed, it is the speed of the rotor with respect to infinite bus voltage. Okay, now if you take the second derivative d2 delta, sorry, d2 theta dt2, then it will be d2 delta dt2, because now omega s is constant, so it will be d2 delta dt2. All right. Now, previously we have written this, that I alpha equal to TA. I alpha. What is I is moment of inertia. Alpha is the angular acceleration, that is equal to TA from mechanics. You know this. Torque equal to moment of inertia into angular acceleration. This is no. That means accelerating torque means moment of inertia into angular acceleration. Okay. This is known to you from mechanics.
Yes.
You know. So therefrom we can write I alpha. In space of I alpha, we are writing d2 delta dt2, because d2 delta dt2 is the angular acceleration. So I alpha means I d2 delta dt2 equal to TA. Okay, TA means input power, input torque minus output torque. So what is input torque? It is input power minus um, rotor speed. And what is the output torque? It is output power divided by that rotor speed. Okay, rotor angular speed omega. Or we can say that I omega d2 delta d2 equal to pi minus pe, means pa. Or I omega, we are writing I in place of I omega, we are writing m, because we are defining angular momentum as the product of rotor angular speed into momentum inertia. Okay, so m d2 delta dt2 equal to pi minus p equal to pa. This is the desired expression. This is the equation that is representing the dynamics of the rotor of the synchronous machine, and this equation is popularly known as the swing equation of synchronous generator, swing equation of synchronous machine rather, because the same expression is valid for synchronous motor as well. If you want to analyze the stability problem of synchronous motor, then this equation will also be applicable. Okay, so this is what we have derived here. Is it clear?
Yes, sir. Clear, sir.
So now, as I already told you, how to analyze the stability problem. You have to solve this equation basically, because when a disturbance is there, then an accelerating power will be created. Maybe the input power will be greater than the output power, or input power will be less than the output power. That means PA will be either positive or negative. Then what is the impact of this PA on the speed of the rotor, on the angular position of the rotor? To know that, you have to solve this expression. There is no other alternative. So you will be solving this, and when you will be solving this, you will be actually having this type of solution, either this type of solution, or this solution, or this solution. How we shall be explaining, or how we shall be interpreting this solution, that we have discussed that if the solution is observing to be like this, then this will be a case of stable situation. If the situation will be solution is like this, then this will be a case of unstable situation. But sometimes solution may be of this type. It is initially showing stable condition, gradually it is becoming higher and higher peak, then it will be unstable. But from the initial variation of delta, it will be appearing to be a stable case, but gradually becoming unstable. Why it is gradually becoming unstable? Because this type of situation happens in case of large power system, because in case of large power system there are so many generators, there will be oscillations, there will be swing between group of generators, between individual generators, okay, between generators in one location to generator in other locations. Okay, so it is said that there are so many modes available in the large power system. So there, analyzing the stability problem will be rather more complex. Okay, but those type of situation we shall be avoiding now, because we are starting to understand the stability problem. That means we are at the beginning of the problem only. That's why we shall be assuming that ours is a case which is like this case 1, or which is like this case 2, not the case 3. That means ours is a simple power system where there are no other oscillations except the oscillation of the generator with respect to large power system, with respect to infinite bus. That's why we shall be assuming that ours is a situation when a generator is connected to an infinite bus. So if this is the situation, then there is no question of having this type of problem, case 3 type of problem. Could I explain? So there will be no case 3 type of problem. That's why we shall be restricted to analysis where this case 1, where the first swing will determine the stability, or the first swing will determine the instability of the system, will be applicable to us. Okay, and a simple method we shall be applying to analyze the stability, because our initial attempt will be to understand the problem. Okay, what is the problem, how it can be actually controlled, what are the factors that influence the stability. To understand this, it is always better to start with a simple situation, and that simple situation will be to consider a single generator connected to an infinite bus. And for this situation, the stability or the solution of the swing equation that will be valid will be either of this case 1 or of case 2. Am I clear? Is it clear? Could you understand this?
Yes, sir. Yes, sir.
Yes, sir.
So that's why we shall be assuming that we shall be interested to understand the stability problem. Some from here, then we shall be moving towards the development of equal area criterion, because equal area criterion avoids that solution of the numerical solution of the problem. Numerical solution, obviously, if we apply numerical technique, you can solve. But that will not give you insight of the stability problem. We first initially are interested to develop an insight, interested to develop the understanding of the stability problem. That's why we shall be deriving this situation first, deriving this relation first, the condition for equilibrium criterion, that we shall be discussing in our next class. Okay, not now, because I should not start this one today. Rather, I shall be discussing starting this in our next class. Okay, is it clear?
Yes.
Yes, sir.
So, if you are having some more question, then you may ask me. Then in the next class, I shall be starting with this actually drawing first, because I shall have to explain this, and then moving to the mathematical derivation, where a criterion called the equilibrium criterion will be applied, and this will be, then you will find that this is a very simple and very interesting explanation, or interesting analysis of the stability problem, which may be easily applied and easily understood. Okay, all right. Now let me go back. Let me start to call your names here. Roll call. And if you are having any question, you may ask me. Otherwise, I shall be making roll call and finish today's class. Okay. Ali Hamzan,
Present, sir.
then Omrita Dotto,
Yes, sir.
then Ankit Joshwal,
Yes, sir.
Orijit Pal,
Yes, sir.